consider the electromagnetic effect, it is on the left side. So we only see like here, like here, and we don't see like the different modulation along the edge, But when we consider the electromagnetic effect, you will see at the edge, you will see some modulation here, and also the dip in the center. And this is closer to reality. And that's why we whenever, later on we may or may not have time to talk about simulation. When we do the simulation, we always, especially for like a high resolution one, we need to consider like a 3D mass effect, because that's what we see at real exposure. And not just that, it also shows that you will see like the best focus shift, and when we do the 45 nanometer line space using a 10-year phase shift mask. So this is a kind of inaccurate approximation. We call it Kirchhoff flat mask. Means that the mask is very thin. But when we do like the rigorous, more accurate simulation, consider electromagnetic effect, consider the thickness of the mask, then you will start to see the best focus shift and also the edge effect. Yeah. So also that's one thing. And for when we go to the OPC, there's two groups of OPC we need to talk about. One is called rule-based OPC, and the other is called model-based OPC. Rule-based OPC basically give you a table, and the table will tell you that if you have a line and space and certain combination, how would you apply? Okay, here I give you an example. If here the line, this is line, this is a space. Okay, if the line is 0.3 and space, the space is 1.5. This line is 1.3. This line is 0.35, and the space is 1. Okay. So then you need to use this one and this one. So this edge will need to minus 0.024. Okay. On the other hand, if this is 0.35 and this is 1, 0.35 and this is 1, and you need to do the plus and 1. Okay. Let me plus and minus. What does that mean? So plus, so if your design here is say 0.3, okay. So usually this is plus, this is minus, because this minus means make it smaller, okay, and plus make it bigger. So say that the space here is 1. Okay, so we are looking at this one and this one. And here the line is 0.3, and the space next to that is 1. So it's a line is a 3, space is 1. So you need to go down here. And minus 0.024. So you need to go this way, because negative is this way. Okay? And on the other hand, here is 0.35. The line is here, and the space next to that is 1, right? This is 1. And it says that you need to positive 0.1. So means that the positive would go positive this way. Means that make it wider, and the negative will go this way, make it smaller. So this edge need to go this way also. Okay? And what does it do? Is make it plus 0.01. Okay? So this is all depend on the edge. Okay? Because we're dealing with this one. So for this one, if just assume here is a 1.5. Okay? This is another line. So then this is 1.5 space. And then this is 0.35. 0.35, 1.5. Then you need to plus 0.004. Then you need to go this way. Because as I say, make it wider is plus, make it smaller is minus, right? So this one it will plus 0.004. Okay? So they just move the edge, depend on the space that next to it. Okay? So that's how they make a table like this, how that works. Okay, so it not necessarily like change the CD. It only change one side. Okay, it doesn't know the other side because it does not know what's the space on the other side. So the rule-based OPC is like working like this. So there's a plus or minus, and make it wider or make it smaller. Okay? So that's a rule-based OPC. However, this one usually is okay for 1D scenario. Okay, you can imagine we're talking about this one, and it was okay for a while, but what if your line is like this? You can say here, that's okay. You can check the line here, the space here. Okay? But how about here? You know the line here. But how about the CD? Is the space here? Or the space is here? Okay? So for two-dimensional patterns, the rule-based OPC will become weak, right? Like here, for example, you know the CD here, but how do you judge this one, right? Your line is here. Your space is this one. It's not in the same direction, right? How do you judge or making a rule like this? Do you use a line this way, or you use a line this way? Okay. So rule-based OPC has its limit. Usually they make a table like this only for 1D patterns. For 2D patterns, we really need to use model-based OPC. Okay. So that's the reason that OPC is gradually move from rule-based OPC to model-based OPC. Okay. So for model-based OPC, basically they need to do a lot of segment. They will do the dissection, and then at every edge, okay, this is a corner, so they make a kind of do the dissection to like a different edge, and the edge, the center of the edge, they have a target point. So we can see that here is very long, so they only have a they consider they will just move up and down for the whole segment. So for each target point, they only try to do the move up and down based on this one. And each one they do to try to see what's the environment, and they put into the computer to consider like all the environment. Like they see these kind of corners and target the neighboring target point to decide if this target point need to move up and down, up and down, up and down. So we will have a lot of jog. Yeah. Basically, for this job, they will decide oh, do I need to move in or out, like I just showed you. For this one, do we need to move out or not? For this one, do we need to move out or not? Okay, so they just based on all the segment, and then they do the whole segment move up and down. Yeah. And they put all this into the computer and then try to do like the calculation. First, the second order approximation, and then give you the final, the mask, what it should look like. Okay. So this is what model-based OPC look like. Okay, and as you can see that it will be very computation intensive, and so it takes a long time to do it. So So the red line here is basically the initial design, but they would change all the segment, move up and down, and then give you the final the mask after OPC. And so after OPC is a black contour like here. But as you can see, it like move out a little bit over here to compensate the line edge shortening, and maybe does not move here, and this will come in here to compensate for the corner rounding. Okay, and at the end they will add like we call it a wave function, and then they give out the cost function of these. The reason is try to minimize the cost function because there's a thing we call it EPE, edge placement error. Yeah, because once they, I mean, if they don't do any OPC, this is the design. Okay, the black is design, and if they don't do any OPC, this is what it ends up with. And then for all the cut point, the target point, they will do the calculation. This is the final contour, the location, and this is the target area, and the distance is we call it EPE. The larger, the worse, right? If you have a larger error, means that EPE will be large. So you add all this up, and then you become your cost function. Ideal case, right? Ideal case, EPE will be 0. Everything will just go along this way. EPE will be 0. Cost function will be 0. Cost function usually won't be negative because you see the square here. Cost function plus or minus got squared, so it's all positive. And so cost function, the ideal is 0, but usually it will not. And when we do the OPC, basically we try to minimize the cost function. So we compare like a 2 OPC result, and at the end we can say OPC 1 is better than the other because it has a lower cost function. Okay? So we try all different algorithms is try to make cost function low. And besides that, we will add like we call it stress, because you can see here. So OPC had 2 parts. One is moving the target point, and the other is add the thread. Because you can see here, this is isolated, and isolated usually have a small depth of focus. And small depth of focus means at the out of focus, the CD will become very weak, means very small. And so they will add this one, try to make this isolated or semi-isolated area, the CD become wider. And so they'll add a thread, maybe 1, maybe 2. So try to make sure the cost function is low. So the OPC, the ultimate metric, how to measure if OPC work or not, is the cost function is lower than spec or not. Okay. For example, if this is 10 nanometer and our OPC target is say 1.5 nanometer, 1.5. So they will add like maybe like a 20 target point here, and then they calculate what's the EPE and do this one, and probably a lot of time they will divide it by the length, the perimeter, and then say that, oh, this is less than 1.5, so this is within spec. And maybe if it is above 1.5, it is out of spec, then you need to redo your OPC model again. try to make it small. Go within the spec. Okay. And next one is LCC, and it is a kind of short for lithography compliance check. Yeah, and this is a simulation tool that to check the layout. So to check the related defect before putting to the mask. And there's two things to check. One is we call it like basically it's wafer litho wafer compliance check, and the other is a max rule check. So one is a LCC and one is a MRC. And so LCC is check if the photoresist contour is within the range from the design target. And MRC if there's a problem with post-OPC mask that can be done, that can be done by the E-beam or not. When they do the mask making, a lot of time it is E-beam. Is it okay to do the E-beam writing or not? So it is MRC is doing that. And so this is a kind of like the flow chart for the mask. Okay, so we have the mask layout, and then we do like the rule treatment, like basically like rule-based OPC or doing at the thread or model-based OPC. Model-based OPC probably doing like over here, or rule treatment, and then add the thread, and then we do the like a model-based OPC. Then we take the after the OPC GDS, and then do the LCC and MRC, and then we fracture that before we making the mask. Okay. So LCC actually always done after OPC. LCC and MRC was done after that, and also need to check before we making the mask and before we even doing the OPC. Something is I think it's funny, but it happens. Is for example, for layout engineering, right? And ideally, it should be kind of a line like this, and then in reality, maybe he's tired, and maybe he's something. Then he will do the layout like this. Okay. So that's something that need to be checked before they do the OPC. There's a software doing like a DRC check or LVS check. They'll find out something like this, or something like this. Initially, it should be a straight line, and then they probably do it in 2 segments, and it is so small. Maybe it's only 1 nanometer. If you don't look at very closely, you think it's connected, but it's not. Okay, so before doing the OPC, they need to do this kind of dummy check. Make sure all the lines are connected and without anything funny like this. Because OPC or like the rule probably think you are trying to make these without knowing that this is a mistake done by layout engineer. Okay? So a lot of things need to be done before they're doing the OPC. Okay. And okay. This will come back later to see. This is some like math logic. We'll talk about that later. Okay? So here, give you an example. Okay, so this is like an LCC result. Okay, so they'll highlight here, say that here at the LCC check, this is a hotspot. It's a hotspot because this is isolated. This is semi-isolated. Okay, so we need to try to fix it. One way to fix it is make all this line longer, just parallel to that, and then this hotspot will be gone. So the blue area here is the so-called hotspot, and kind of design or layout engineer will come to litho engineer and ask you how to fix a hotspot before doing the tape-out. So as I mentioned, after the OPC, we need to do the LCC and MRC. And if it failed, or you have like a 10 hotspot, then you will go back here to change that, and then go through that, and to do the LCC, MRC again. And until all the hotspots are clean, before they move it to the mask making. Okay? So this is something that needs to be done, and this is just an example of hotspot. And a lot of time it is just because it's isolated. Okay? And one way, as I mentioned here, is make it dense. And sometimes we just make it wider. There's several different ways to make it. Okay? So hotspot fixing flow. Okay? So as I mentioned, so we do check out the LCC, and then if we don't find hotspot, then it is clean. But if we found hotspot, they need to go out to layout team, and then to do like a modification, and then do OPC. And after OPC, then they will check with the LCC again. And then if the hotspot removed or not. If it's removed, then it's okay. If it's not, then go back again. Do several iterations until all the hotspots are gone. And this is an example for MRC. So this is original layout, and then this is kind of after MRC check. And as you see here, no problem. Oh, there's a problem. Here is short. Okay, you can see it should be separated, but here is short. Okay, and here is the space is too small. Okay. So both of these, the LCC are okay, but here, both of them here, MRC is not okay. So checking LCC is not good enough because LCC just means that wafer is okay. That doesn't mean that you can make the mask. The E-beam will tell you that this is too close. So there's a high risk that this E-beam writing will make this one short. This E-beam writing will make it short. Okay? So it will not let you doing this, for example. Okay? So before we do the tape out, both LCC and MRC need to pass, need to be good. Okay. So maybe now is a good time to take a short break. Okay. Next hour we will talk about EUV. Future, you probably need the knowledge of EUV, but at the same time, we'll be able at this class first time to talk about tool. Okay, in the past we only talk about process, right? What is OPC? Like last week, what is illumination? What is photoresist? But everything happened in the tool. Okay. So before I go to EUV, maybe I'll just do an introduction about the tool itself. Okay, so as you can see that the tool is huge. If you go to the fab, it is huge. And high-NA is even bigger. And in the past, the illuminator is not so big, but right now the UV, the light source is gigantic. Okay? Later we'll talk about that, but basically let's kind of dial back and look at the normal 193-248 I9. Usually it is a light source coming here, and the wafer, this is a lens, but in the old time, lens is just like a camera. It's a lot of refractive lens. Okay, the light goes through the lens. Okay, but in EUV, it's not refractive anymore. Everything becomes reflective. So it becomes mirrors and bounce back and forth. Okay, so that's the difference. And the source in the vacuum. Okay, for EUV is in vacuum, but in the old time, everything in the air. So everything in the air, and for immersion, wafers in water. Okay, so that's a different. And the other thing is that usually radical is like on the top, wafer on the bottom, and lens in between. So both radical and wafer are like traveling on the opposite direction. And so they're kind of like flying. And so a lot of time, like SM will need to tell you how synchronized the flying is like. Okay, so they need to synchronize the flying so that the image fidelity will be high. Okay, and there's a illumination system that the light coming here, and as I told you, they will go into the OAI or go to conventional. So they have a mirror to tell the illuminator, do they give you the conventional, annular, or quasar C-quad. So there's an illumination system give you that. But for the EUV, the major difference is that the mask, the lens is all become reflective. They're all mirrors. And each mirror is about, you probably see, about 67% reflection. Okay? And everything in vacuum. So the wafer coming in, and it is in the vacuum. And of course, we talk about light source a lot, wavelength. So in the past, it's either 193, 248, or 365 I9. And now the light source is 13.5. So the reason why it is vacuum is that this is a soft X-ray. And so if you don't use a vacuum, water, like a water vapor or oxygen, will absorb the light. And then, so there's no light. If this is no vacuum, this is air, the light will not arrive at the wafer or not even on the mirror itself. It will get absorbed by the oxygen. So that's why everything needs to be in vacuum. Okay? And EUV, stands for extreme ultraviolet, but actually is X-ray. Okay, 13.5 is a soft X-ray. Okay? And the design, right now, the first generation, when I was still with Centis, we were using 0.25 NA, and now right now the current generation EUV is using 0.33, and both of them are like 6 mirrors, and so the current high-NA EUV is using this one. So there's an opening in the center. So still 6 mirrors. They don't use the 8 mirrors. So there's a called central obscuration. So as you see, this is solid, means there's no hole in the center of the lens. And there's a white here, means there's a hole in the center of the final lens. So there's no light going to the center. There's no light coming into from the center of the final lens. Okay, and so center obscuration for high-NA EUV, and as I mentioned here, the NA is 0.55, and right now the HVM is 0.33, and the Alpha tool, the one that Centis and Toshiba bought, is 0.25. Okay. So there's a kind of like a 3 generation of the lens that we see. Okay. And EUV power source. Okay. Initially, there's 2 competition. One is called DPP, one is called LPP. And DPP was using plasma to arc. Okay, so this is a tin. SN is stand for tin coated, and it is a rotational disc. And the light goes through here, and then it is a foil, and the light kind of glazing through all these mirrors before they arrive. We call this is IF, intermediate focus. And like Wushu, Wushu is a company that is doing that. But the problem is that they have trouble scaling up the power. Okay? And so there's a debris mitigation, means the debris basically is a tin. The tin will come out, and then we use a foil to kind of collect all the tin debris. The debris is tin. And so this is a high voltage. They use a high voltage to ignite the tin plasma. Okay? In this way, they can generate the EUV. But right now, this is not in production. This is basically used for inspection. The inspection tool they are making. Wuxi right now only making inspection tool, and they're cheaper. Okay? And this is at that time only Cymer and Komatsu. Right now, Gigaphoton is making this one. So basically, they will have a tin droplet coming down, and then the high power CO2 laser kind of light up the tin droplet. So then they will come out with EUV 13.5 photons. And this is, we call it collector. So the light coming out, of course this direction is okay, but the light coming out from here will get reflected and focused at the IF, intermediate focus. Okay? So it is a CO2 ignite the plasma to produce EUV. And the debris mitigation is they use a hydrogen, and they basically have the collector over here. So they collect the tin over here. And Komatsu Gigaphoton using superconductor magnetic field, superconductor magnetic field to direct all these tin droplets. And but as you can see, a lot of tin will get coated at this collector. So SML at that time, we see them spend a lot of efforts how to clean this one. And at the end, they use a hydrogen gas to clean the collector. Okay? So they call it like this is a light source chamber, or they call it a vessel. Okay? As I told you, the debris mitigation for the collector, they use a hydrogen. They use a hydrogen purge so that the tin will not coat it so fast at this collector. Okay? So as you can see here, the droplet, the tin droplet generate here and then collect here. The droplet collector. And then they kind of have the droplet size, if I remember correctly, it is about 20 to 30 microns. And CO2 laser shining here, and then burst to, actually later we'll talk about that, shining on here, and then the light coming here for intermediate focus. Okay? And they also have a kind of a camera here to target what's where the droplet is, so that the light can synchronize. This is a pulse CO2 laser. They can synchronize the speed of the droplet so that they can generate UV display. And the EUV exposure, okay, it is a reflective. So the mask will have a multi-layer of it's called MOSI. Basically, it's a molybdenum and silicon. Yeah, it is about 40 layers of molybdenum and silicon. Yeah, like alternating to generate enough reflection. And then there's an absorber. Usually it's tantalum nitride or tantalum boron nitride. And then the refraction, and here they will not have the light coming here. So the light coming here and here. Here's we call it absorber. Okay. So UV reflect from the mask and then absorbed by photoresist and substrate. And then that's how the pattern is formed. Okay. And there's also like a second electron that is random. And the other thing is that the number of photons is much less than 193. So a lot of time we see a lot of noise. We call it sharp noise. And that will cause like LER because of the sharp noise. Okay, so for the mask, this is a cross section. And it is a silicon molybdenum. And this is kind of the schematic of the mask. So even mask and the lens, everything is in mirrors. So UV from the source and then go to the mask and then go through 6 mirrors. And then at the end, go to the wafers. And over here, if you take it out, you will see that like molybdenum and silicon, and here is 6.7 millimeter. Okay. But still, it's a 4-to-1 reduction. Okay, so say that the feature is 30 nanometer, so over there will be 120. Unmasked will be 120. So why do we use silicon molybdenum? Okay, this okay, so there's several candidates. Okay. As you see here, the EUV is at 13.5. Okay, there's a tungsten, there's a molybdenum, there's a B, I don't know the name, and there's a silicon. Yeah, so for attenuation, okay, yeah, they need to be low. So these are good candidates between 10 and 15. Okay. Yeah. So they say that molybdenum BE has even higher reflectance, but this is toxic. So at the end, they choose a molybdenum silicon. Yeah, those 40 layer has 70% reflection. So they want to have this as high as possible. Okay? They want this to be high as possible. So this one is chosen. Okay? So you can see silicon. Yeah. The B can be higher than that. Yeah. Due to safety. So here is some results. Okay, so one is, for example, overlay. Okay, remember we talked about CD. CD variation, I talked to you about intra-wafer CD uniformity, like inter-wafer CD uniformity. So here is a lot, but it is overlay. So from lot to lot, overlay result. Okay, so you can see that this is dedicated chuck overlay, and this is a match machine overlay. So means one is a single. You can consider one is single machine. Only this EUV number 1, for example, and then you put different wafers, different lot, and then to measure the overlay. So you're using the same lens, right? You're using the same lens, but if it is a matching machine overlay, so you have EUV machine number 1 and EUV machine number 3, and then you take wafer from number 1 and wafer from number 3 and measure their overlay errors. So they will have a different lens, right? They have different lens, and then they measure overlay. So this one usually will be higher. This one is smaller. Okay? If you remember overlay, remember we have this rotation, this translation overlay. But if you have the same tool, usually the signature will be the same. But if you have different machine, the lens will be different. Okay, so they will have later on you will have the spec for X and Y, and also you usually try to pick out what is the largest. Right? This is from day to day. You can see it will change, and this is even like a match machine overlay. Okay? So as you can see, like single machine overlay, they can reach like about 1.3, and match machine overlay is 3.4, and it is nanometer. So in a sense, it's pretty decent. Okay, and you can see here the full wafer CD uniformity is 1.5. This is for scanner qualification, and best exposure dose. Best exposure dose is 15.9, and energy latitude is 13% POF 160, and this is a printing result, 22 head pitch, and they show their result. They can even go down to 13 nanometer head pitch, and for the whole, they can go to 18 nanometer head pitch. And with that, they will be able to do the EUV with a spacer. Okay, so for ultimate resolution, they are even like kind of combine the EUV as a main draw, and then do the spacer on that to show the ultimate resolution. So one thing I have to tell you is we call it, they use a so-called pre-pose technology. And this is only for EUV. Remember I told you about droplet. Okay, so this one, the blue one, is a droplet. So the blue circle here is the droplet. So it will come out from the droplet generator and it will come down, and then at the end you will have a droplet catcher down here. But during the kind of the ignition of the EUV, actually there's two lights coming here. One is called pre-pulse, one is called main pulse. So pre-pulse basically is remember I told you this is about like a 20 to 30 micron, and they have a pre-pulse to kind of explode the one and make it like a cloud. So you become from like a 20 to 30 to be maybe 200, become a 200 cloud. So it will be much bigger than it itself. Okay, and then the main pulse will do that. And the reason is that they do this experiment. Actually, it was experiment, and then they find out that the conversion efficiency is much higher with the pre-pulse technology. What is the so-called conversion efficiency? Conversion efficiency is that the energy produced by the EUV divided the energy of CO2 laser. Okay, so say that you have 100. Say that you have EUV. So the CE is so is the EUV energy divided by CO2 energy. Okay? So you can see here, it is about 3%. So if you have three, let me tell you, usually they want to have EUV power is about 150 watt. If it cannot have 150 watt, it cannot have HVM. Okay? And CO2 power. Think about it, assuming it is 3%, so it is a 3 over 100. Okay? So what does that mean? The CO2 will have 50 times 100. So CO2 power need to have 5K. Okay? And you probably can check it out right now. The EUV energy is probably more than 150 watt. So CO2 laser is probably either 10K to 30K watt. You can see how high the energy is. So that's also the reason why they say EUV itself need a power generator, and EUV is very power hungry. The reason is that the CE is so low. Okay, and also right now a lot of AI chips is using EUV to generate. And they say that pretty much wherever you have an EUV tool, you probably need a power plant next to TSMC or next to Samsung or Intel. And eventually, they're talking about that EUV, not EUV, AI is not gated by company like TSMC. It's pretty much gated by power. Okay? A lot of people do the prediction, including ASML, they give the warning, okay? Because the AI is gated by EUV, and EUV is gated by power. So eventually, AI is gated by power. Okay? So in the future, you need to think about that when you are, if you are a decision maker and you are trying to kind of scale up your production, you need to think about power, especially for EUV. Yeah, because the background is basically on this formula. You need a lot of CO2. You need a very high power on the CO2 laser. That's the reason. Okay. And go back here. With the pre-pulse, they can increase that to 3%. Without pre-pulse, it is below 2%, if I remember correctly. And the theoretical limit for this mechanism is about 5.5. Yeah. If you have perfect conversion, it's about 5.5 conversion efficiency. So for EUV, this is still a special proximity effect. Okay, we call it shadow effect. It's because the light of EUV coming in 6 degrees. Okay, so if it coming on the like a perpendicular 90 degrees, they won't be like this. But because it coming into 6 degrees from like a complete vertical, okay? So they will find out if you have this vertical line, no problem. The CD will go to here. But if you come to here, then there will be shadow, and the CD will be larger. So you can see that this one, the pink one, the CD will be larger than the green one. And also, the best focus will shift, okay? So you can see horizontal will show like the CD will have a slightly 5.2 nanometer larger than that. So need to be correct, okay? Correct the horizontal and vertical difference. And CD bias is 3.5 due to the shadowing effect. Okay. And here, pretty much show the result. But right now it's much better. Okay, so about 5 years ago, they show off this EUV result. They can go down to like about 10 to 13 nanometer. Okay, there's a company called Impria. I don't know if you can see it clearly or not. This company is still around. Okay, this company called Impria, and they can do very high resolution image, but they're not CA photoresist. It is we call it metal containing resist. They're photoresist containing silicon, so they cannot do chemical amplify. They need a high dose. They need a high dose to produce the very straight lines. Okay, but at that time, they are kind of the champion to be able to produce very small lines. And for this one, just want to mention the pattern they want to show off. This is for like a stagger for flash. So stagger line, stagger contact holes, and for DRAM, the AA layer, they have we call it like a brick wall. Okay? And this is for SRAM, the 16 nanometer node. Okay? And what they use, as I told you before, if they want to do the vertical line, they want to use a dipole. Okay? Yeah. And they show big depth of focus, and for 22 nanometer for like contact holes, so they can show the printing, single printing can go down to 17 nanometer. Okay. So as I told you, CAR basically is a chemical amplifier resist, and you can see the impria. This silicon containing resist have a much less LWR. Okay? So that's why they want to show that. But at the end, people still trying to improve the photoresist and then go back to CA, chemical amplifier resist. So this is just a schematic. People still use chemical amplifier resist for EUV. As you see, the protons, like one proton will produce like 3 protons during the PB, and then doing that. Okay. And this is the things I mean, we try to do during your experiment, but we didn't have time. Trying to change the PEB temperature, and you can see that, and this is using E-beam to do the EUV photoresist exposure, and you can see that when they increase the PEB temperature, then they can kind of improve the printing much better. Okay. So on the X is a different E-beam dose. On the Y is a different PEB temperature. Okay. So yeah, I mean that's something that initially I want you guys to do during the experiment. Yeah, change the dose or change the PEB temperature. So this is initially the ASML, they call it roadmap. Okay, so on the EUV they start from 0.33 and then they go to 0.55, and they start to ship the production tool this year to Intel especially, and then TSMC. And now you can see that they are going up to 200 wafer per hour. I mean, pretty much the same even for EUV. And the resolution is going from 13 to 8. But how they show 8 actually is going from the imperial resist. Because the imperial resist does not have this acid diffusion, so they can show better resolution. And for the high NA, there's some change over here. They only use half of the field. Okay, the photo mask. The dimension of photo mask is 3326. That's the dimension of photo mask. Okay? But for high NA, they only use half of this. So this is a 16.5. Okay? 16.5. So they only use half of that. The reason is that, as I told you, the high NA, they use a central obscuration, so they cannot use a full field. And also, on one hand, on the y direction, it becomes AX. On the X, it's still 4X. Okay? So what does that mean? Means that if you have a contact, just for the simple, make it 20 by 20. Okay? The contact is 20 by 20. But now, I mean, in the past, for low NA, I mean 0.33 NA, it should be what? 80 by 80. If NA is 0.33. This will become 160 and 80. Okay, so this is our wafer. We want to print 20 by 20, and because the ratio is 4x, right? For 0.33 NA, the ratio is 1 to 4. So on the mask, on EUV mask, the contact should be times 4, so 80 by 80, right? But for high NA, now in the y direction is 1 to 8. So the contact becomes 160 on y direction. On the x direction, it becomes 80. Okay? So for high NA, there's a lot of things need to be changed. This is just one example. And second example that I learned this year is that we call it stitching. Okay? Think about it. Right now, if you have a mask and only do half of the exposure, okay, what does that mean? Means you'll do exposure number 1 here and exposure number 2 here. Okay? So that means if you have a line here, your first exposure will only expose this part. Then your second exposure will do this part. Okay? So very likely your exposure may look like this. You will have some stitching problem. Okay? So stitching is the one thing to kind of need to be corrected or need to be take care during this one. Or when you design the mask, you need to avoid it goes through these 2 areas. so that it does not need to do the stitching. Okay, so this is something new that I learned this year, and you probably need to face in the near future. So we talk about like the EUV, the issues that all these years we need to take care. It is like an R&D project that always, if you are doing the EUV process development, that you're working with, for example, ASML, then you need to talk about like a source power, right, to improve the throughput. If you work with a resist company, the photoresist, how will you be able to handle a nanometer, right? Are you using silicon containing resist or using car resist? And then you go back to do the mass inspection. Mass inspection has two areas, like blank. Is there any particle on the blank before you put down the 40 layer of the MOSI, right? And also, right now, a hot topic is pellicle. Pellicle is a thin film above the mask. And right now, TSMC still trying to get something, but still not in the production using pellicle. Okay? And high NA mask issue, as I mentioned, right? How do you do the stitching? And how do you handle like asymmetrical? Why is AX? X is 4X, and also PSM, and also process integration. That's if you're in the EUV team, that's something that you will face. So here, as I told you already, how to improve the source power, because that's related to the throughput. And how do you get the defect-free mask blank? And how do you inspect the mask that has pattern on it? And resist diffusion length. If you want to print a nanometer, that diffusion length will adds up and then show the process. Okay, so let's kind of summary the OPC, the contamination, the source power, right? And photoresist, If we go down to about 10 nanometer, the diffusion length is very troublesome. And photomask. How to inspect the defect, and once you have defect, how do you repair and pellicle? So that's a challenge in the EUV lithography. This is conversion efficiency number. We don't need to talk about it detail. As you can see, this is very small, and they just use a pre-pose to improve the conversion efficiency. So I think, that's what we have. Okay. So let's take a short break, and we come back in 10 minutes